Hello. In this video we're going to look at a matrix which happens to be a symmetric matrix, a specific one. So the matrix is 3, 2, 2, the second row is 2, 2, 0, and the third row is, oh dear, sorry, this is not visible, there we go, and the third row is 2, 0, 4. And what we're going to do with this matrix is the following. We're going to verify that the three vectors that I'm going to write out now are eigenvectors of this matrix, and moreover we're going to find the eigenvalues for which these vectors are eigenvectors, and also verify that that these vectors are orthogonal to each other. So this is the matrix A, and the three vectors that I was talking about are k1 equals the column vector minus 2, 2, 1, k2 equals the column vector 1, 2, minus 2, and k3 equals the column vector 2, 1, 2. Okay, so how do we carry out the first task, which is to verify that these column vectors are eigenvectors of the matrix? Well, what is an eigenvector? It's a non-zero vector such that A times k, it's a non-zero vector k, such that A times k is equal to lambda times k for some real number lambda. So to verify that each of these are eigenvectors, what we need to do is to set up an equation like this, and we need to be able to find a lambda that fulfills this equation for each of them. So there will be three equations where we need to solve in each case for lambda. And of course, the way we're going to do this is quite easy actually. We're simply going to evaluate the left hand side and then compare the resulting column vector with the original vector, and then see if an appropriate lambda can be found or not. Okay, so that's one way. The other way is to use a bit of theory from the eigenvectors and eigenvalues, where we can immediately write down a system of linear equations and in terms of lambda, and then solve it for lambda. Okay, so let's begin with k1. What is going to be A times k1? So let's have a look at that. It's just a matter of multiplying the matrices. So 3 times minus 2 is minus 6, plus 4 is minus 2, plus 2 is 0. So once again, 3 times minus 2 is minus 6, plus 4 is minus 2, and plus 2 is 0. Okay. Now let's look at the second entry. So it's supposed to be a column vector because we've got a 3 by 3 matrix multiplied by 3 by 1 matrix, and the result of this will always be a 3 by 1 matrix, right? So what about the second entry? 2 times minus 2 is minus 4. 2 times 2 is 4, so they added together, it gives 0. Plus 0 times 1, it is 0. And then 2 times minus 2 is 0. Minus 4 plus 0, because 0 times 2, and then plus 4, it's 0. So you see, what we get here is a 0 vector. And now this needs to be compared with the original vector k1. And in particular, what we need to see here is whether the 0 vector can be made to be equal to some lambda times the vector minus 2, 2, 1. And of course here we can see here that what we need to do is to take lambda to be equal to 0. Remember, an eigenvalue can be equal to 0. It's the eigenvector that cannot be the 0 vector, but the eigenvalue can sometimes be 0, and this is exactly what's happening here. Of course, conceptually, or rather geometrically, eigenvalue being 0 means that the linear map corresponding to the matrix, what it does to this vector is that it squashes it down to the 0 vector, so it in a way kind of kills the entire line passing through this vector, where all of the vectors on that line are going to be squashed down to a single point, the origin of the coordinate axis. Okay, so we found that we verify that k1 is an eigenvector, and we've also found the corresponding eigenvalue. And the same should be done for the others. Now, so what's this other method I was referring to? Well, the other method is to make note of the fact that this equation can also be rewritten as a minus lambda I times k equals 0. So the second equation actually plays an important role in the theory of eigenvectors and eigenvalues, as you may remember from last week, where the determinant of this matrix here is equated to 0, gives the so-called characteristic equation, which allows us to find eigenvalues. Then when we find an eigenvalue, we put it into this matrix, we solve the system to get the eigenvector. But in this question, we are already given a potential eigenvector, so it's not that we need to first find lambda and then k, it's the other way around. We already have a k, and so we have to find a corresponding lambda for it. So what we can do is to simply compute this matrix here, write it in this way. So what will this be? I is an identity matrix, so it has diagonal entries lambda. So when I subtract that from A, I will have 3 minus lambda, 2, 4, and then the other entries will be just the same as they were before. And now I multiply this by k, which is 1, 2, minus 2, and I want to get the 0 vector. That's what this 0 here stands for. That stands for the 0 vector. And so the question is, I forgot to subtract the lambdas from the other diagonal entries. So the question is whether such a lambda can be found so that this product is 0 vector. And to answer that question, so this is just another way of answering a question like this, where in the previous case we used the more standard way of just applying the definitions. So we multiply this out, and when we multiply this out, we get 3 minus lambda times 1 plus 4, 2 times 2 is 4, then minus 4. That is equated to 0, because the first entry of the column vector here then needs to become the first entry of the column vector there, because when the two vectors are equal, this means that the corresponding entries are equal. So the first is equal to the first, second entry is equal to the second entry, and so on. So the first entry is this value on the left hand side, so it's equated to 0. Then the second entry on the left hand side is 2 plus 4 minus 2 lambda, and that should also be equal to 0. Then the third entry is 2 minus 4 plus 2 lambda, and that should also be 0. So now the question is whether there is a lambda which makes all of these equalities hold, and so we can simplify these equalities, of course. We get here 4 here goes away, and we get lambda equals to 3. And in the second equality, we get 6 minus 2 lambda equals 0, and so that also gives the same lambda equals to 3. And in the third equality, we get minus 2 plus 2 lambda equals 0. unless I made a mistake somewhere. Let me just double check my calculation here. So we had, because I'm kind of getting an answer that I wasn't expecting. So 2 is the entry there, 0 is the entry there. Okay, that was right. So 2 times 1 is 2, plus 0 times 2 is 0. So that leaves just with 2. And then plus minus 2 is multiplied by 4 minus lambda. And so that is minus, not minus 4. That's what the mistake is. It should be minus 8 here. Sorry about that. So it's minus 8 plus 2 lambda. And so that gives lambda equals 3 again, because on the left hand side here we get minus 6, and when we carry this on the other side we get minus 2 lambda, and so lambda is going to be equal to 3. So in all three equations we got the same lambda, therefore that lambda value works for the entire system, and that's what we wanted, right? We wanted a single lambda that would work for this equality, and now we see that such value is 3, and so we've answered the question for the second matrix as well. And the answer is that indeed this is the K2 is an eigenvector, and the corresponding eigenvalue is lambda equals to 3. I think that okay, I wrote that down and it's not visible. That's bad. Let me just make sure that my screen is of this size. It should be, so that I don't end up writing things down that are not visible. So let's write down the answer again. So we got that the eigenvalue for the second vector K2 is lambda equals 3. And if you compare these two methods, you see that the first method is much simpler than the second one, although the second one makes use of a technique that when we don't know what the eigenvector is and the eigenvalues are, when we have to find them from scratch, then this technique is very useful. But when we already know what eigenvector is, it becomes a bit of an extra work to apply this technique. So for the third vector, we're still going to apply the first technique because that's a better technique. Okay, so to do that, we need to I need to copy down the matrix and the vectors so I don't forget what they are. So let's move down here, and we've got them here, and then we can here we don't need to worry about the K1 and K2. Now we are left with K3. We want to verify that the K3 there is an eigenvector for the matrix A. And so the way we can do this is, as we said before, we multiply A with K3. So this matrix will be multiplied with 2, 1, 2 matrix. And when we do the multiplication, the result will be, so 2 times 3 is 6. No, sorry, we shouldn't write it down yet. So 2 times 3 is 6, then plus another 2 is 8, plus 2 is 10. And here we have 4 plus 2, which is 6. 4 plus 2 plus 0, so that's 6. And previously we had 6 plus 2, 8 plus 4. No, it was 12 actually before. Sorry about that. So we have 12, 6, and then in the third entry we have 2 times 2 is 4, then plus 0, and plus 8, and 4 plus 8 is also 12. So we get 12, 6, 12, and that of course is equal to some lambda times the original vector, where the lambda is 6. So that is equal to 6 times 2, 1, 2. And so we verified also that the third vector is an eigenvector, with the eigenvalue being lambda equals to 6. So we carried out the first task we were supposed to carry out, which is to verify that the three given vectors are eigenvectors. And we've done that. We've found the corresponding eigenvalues. And now the other task we said we were going to carry out is to verify that these column vectors are orthogonal to each other. We don't really need to do that by the theory. The theory tells us, there's a theorem that tells us that if a matrix is symmetric, then its eigenvectors that correspond to different eigenvalues will always be orthogonal to each other pairwise. So since the eigenvalues that these eigenvectors correspond to are 6, 3, and 0, and since all these numbers are different from each other, we can conclude from the theory that the vectors will be orthogonal to each other. But that's not what we want to do here. We don't want to just know that they are orthogonal. We want to do a calculation where we're going to check on this specific example that they are orthogonal. Well, after all, in the theory we never proved that result as a general theorem, so maybe it is worthwhile at least to check that this is true on some examples. So let's take the three vectors again, and what we're going to do now is to multiply them by each other pairwise, and then get the orthogonality. So what does it mean for two vectors to be orthogonal, by the way? Well, that means that their inner product is always 0. So the three inner products we need to consider here is that of k1 and k2, which is supposed to be 0, and we want to check if it is so or not. Then we also want to check that the inner product of k1 and k3 is 0, and also that inner product of k2 and k3 is 0. Okay, so let's do that. We take k1 and k2. How do we get the inner product? Well, the inner product is defined as the matrix product. So this is actually the same as k1 transpose times k2, where here we have usual multiplication of matrices. So the dot there isn't multiplication of matrices. It would be impossible to multiply these as matrices because of the dimensions. This is a 3 by 1, and the other one is also 3 by 1. But when we transpose, it becomes 1 by 3, which can be multiplied by 3 by 1 matrix, right? So the first line here is inner product, and the second line here is the matrix product. There is no line now. There is. Okay, so the first equality there is equivalent to that equality here, because the left hand sides are equal, and so the same also works for the third equality there. So what we need to do now is to check that the transpose of k1 multiplied with k2 gives a 0. And so, well, what is transpose of k1? This is minus 2, 2, 1, and k2 is 1, 2, minus 2. And when we multiply these together, we get minus 2 times 1 is minus 2. Then 2 times 2 is 4, so that's plus 4. And then plus, well, minus 2, because it's minus 2 times 1 is minus 2. Okay, so this value is the same as minus 4 plus 4, which is indeed 0. And exactly the same way, you can check for k2 and k3. Another way of remembering the inner product is, of course, to say that you just take the two vectors and you multiply their terms, corresponding terms, and then just add these products together. So thinking of it this way, rather than transitioning to the transpose matrix, we can carry out the calculation for the second equality as follows. So let's say now we want for k1, k3, right? So for k1, we're going to have minus 2, 2, and 1. And for k3, we have 2, 1, 2. And now we want the inner product of these two things. And so we can get the inner product directly by the elementary description of the inner product as term by term product, and then the sum of those terms. So we have minus 2 times 2, which is equal to minus 4, plus 2 times 1, which is equal to 2, plus 1 times 2, which is equal to 2. So again, we get 0. And the last case that we want to look at is k2 times k3, and you can quickly see here by the same principle of taking their inner product that indeed the result will be 0. Okay, great. So this completes the example video where we took a specific symmetric matrix and we looked at specific three vectors, and we first of all checked that these vectors are eigenvectors of the matrix, and then also found the corresponding eigenvalues, and finally we confirmed that the eigenvectors are mutually orthogonal to each other. The theory that's behind this, which we didn't use, but still it was an illustration for the theory, so it's worth pointing out. The theory behind this is that the a symmetric matrix, when it has different eigenvalues, all the eigenvectors for those different eigenvalues will always be orthogonal to each other. And so because the 3 eigenvalues that we found here were different, 0, 3, and 6, we know that the vectors must be different, and we just illustrated this by doing the calculations to check that indeed did I say the eigenvectors are different? Sorry, I meant that orthogonal, and we checked that by calculating in each case the inner product that allows us to establish the orthogonality, because by definition of orthogonality, 2 things are orthogonal when their inner product is 0.